let's look at the concept of end behavior, and that's going to help us make the graphs of polynomial functions, which we're going to do a little later in this video. So the first thing I want to do is graph each one of these equations. So this is y equals x squared. Hopefully you remember that y equals x squared looks like the letter U, like this. And the end behaviors occur at the end of the graphs, here and here. That's what we're going to analyze in the first part of this video. And these arrows just mean that the graph goes off upward to infinity in this direction, and same thing with this arrow. It just means the graph continues on upward into infinity. So that's the end behaviors of y equals x squared. Now let's graph the rest of these. Y equals negative x squared is just this graph reflected over the x-axis like this. Those are little arrows there, right there. And the end behaviors occur here and here. Let's look at this one, y equals x cubed. Well, hopefully you remember that that graph looks like this. These are good to put into memory. Something like that. That's close enough. That'll work. And here are the end behaviors. Here and here, right? This one's going off into negative infinity downward. This one's going upward into positive infinity. And y equals negative x cubed is the same as this. It's just this graph reflected over the x-axis. So it's going to look like this. And I'm getting better making these as I practice. This just takes practice. And here are the end behaviors, here and here. Now let's analyze these equations here. First thing I want to do is find the degree of the polynomial. I wrote that down here. And the degree simply means the variable or the letter with the highest exponent. Well, since there's only one letter here, the degree has to be just the exponent itself. So the degree here is 2. So this is a degree 2 polynomial, and 2 is even. So the degree is even. And I'm also going to look at the sign of the leading coefficient. And the coefficient just means what is the x squared multiplied by. Well, there's a hidden 1 there. Let's write it in. So the leading coefficient is 1. And the sign of the 1 has to be positive. When there's no sign, it indicates it's positive. So the sign of the leading coefficient is positive. And I'll put that in here. So when you have an even degreed polynomial, and the sign of the leading coefficient is positive, your end behaviors will always look like this and this. Let's look at this one. What's the degree here? Well, it's also 2, and 2 is even. And the leading coefficient again is 1, that hidden 1. But the sign of the leading coefficient here is negative. So I'll put negative here. So when it's even degreed and negative, the end behaviors go down in this direction. So you should notice that when it's an even degreed polynomial, the end behaviors go in the same direction. They're either going to go upward in the same direction or downward in the same direction. And that just depends on the sign of the leading coefficient. Now let's look at this one. What's the degree of this particular equation, y equals x cubed? Well, in this case, it's just the exponent itself. It's 3. So it's degree 3. 3 is odd. So this is going to be odd. It's an odd degreed polynomial. And again, the leading coefficient is 1. I'm going to put it in there, and it has to be positive because there's no sign. So the leading coefficient has a sign that is positive. So when it's an odd degreed polynomial and the leading coefficient is positive, the end behaviors look like this and this. And here, again, it's an odd degree because this is 3. But the leading coefficient here of 1 is negative right here. So when it's an odd degreed polynomial and the leading coefficient is negative, the end behaviors will look like this and this. And you should notice that if it's an odd degree, the end behaviors go in opposite directions. And to figure out how they're positioned, you need to look at the sign of the leading coefficient. One other thing I want to show you is you should notice that if the exponents are even, the graph, it's called quadratic, it bounces off the x-axis. See how this bounces off the x-axis? It doesn't go through. So keep that in mind when the exponent is even. when the exponent is odd, like in these cases, the graph doesn't bounce, but it crosses the x-axis here and here. So keep that in mind, that when the exponent's odd, there's a cross, and when the exponent is even, there's a bounce. That's going to help us when we make graphs. So let's move on here. Let's make the graph of this using some information we just learned. You should realize that the first step is to actually find the x-intercept. So let's do that. And the x-intercepts of a graph occur when y equals 0. So I'm going to replace that y with 0 like so. And remember, for these problems, the equations are all in factored form. That's going to make it easier. So keep that in mind when we're doing these problems. And factors are things multiplied together. So what I'm going to do to find the x-intercept is set each factor, this factor of x plus 4, this factor of x minus 1, and this factor of x plus 2, I'm going to set them all equal to 0. Let's start with x plus 4. So I'm going to say x plus 4 equals 0. Well, what do we get when we solve this? Well, we subtract 4 from both sides. And you should notice we get x equals minus 4, because 0 minus 4 is minus 4. But I don't want to go through that every time. You should notice that I really just switch the sign of the plus 4 to minus 4. That makes it quicker to find. So let's do it that way. And I'm going to turn that 0 back to a y now. So what's the x-intercept here? We already did that. That's x equals minus 4, right? I just switched the sign. And what about here? It's going to be x equals plus 1. I just switched the sign of the minus 1 to plus 1, and the x-intercept here will be minus 2. And I'll show you where this squared comes in when we make the graph. Once we've found the x-intercepts, let's go ahead and plot them. So minus 4, x-intercept is here. 1, 2, 3, 4. This x-intercept is 1, so I'll go to the right one. And this x-intercept is minus 2, so I'll go to the left 2. Now I have my x-intercepts, and now I need to figure out my end behaviors. So let's do that. So end behavior. And you should remember that we need to find the degree and the sign of the leading coefficient. Now I'm going to show you how to find the degree. It's tricky, but there's a trick. And what you really would need to do is multiply this all out and see what the exponent is of the x. But I'm going to show you a trick, and this works when it's in factored form. So watch how I do this. This x plus 4 really has an exponent of 1. There's that hidden 1 again. It likes to play hide and seek, right? So if there's no exponent with this factor, there's a 1 there. What's the exponent of this factor? It's 2. What's the exponent of this factor? It's not showing, is it? So it has to be 1. So what I can do now is add up these exponents. What's 1 plus 2 plus 1? That's 4. So this is degree 4. It's a degree 4 polynomial, and 4 is even. So let's write even here. Now remember, you can only do this trick for the degree when it's in factored form and when there's no exponents with these x's, with this one, or this one. If there were, for example, an exponent of 2 with this x, it'd be slightly different, the process. Just keep that in mind. Now, what's the leading coefficient here? It's 1, right? It's that hidden 1 again. It likes to hide out. I'll put it in, and the sign of that leading coefficient is positive because there's no sign there. So the sign of the leading coefficient is positive. And now I have my end behaviors. And you should remember, if it's even, it's going to go in the same direction, either up or down. But let's just go back to the chart. It was even and positive for this problem, which is here, even and positive. So that tells me my end behaviors are going to look like this and this. So let's write those in there. My end behaviors are both going to point upward. So I'm going to go a little to the left of this x-intercept and put in my end behavior like so. Something like that. I can get that a little better. I'm going to just slant it a little bit. So there's my end behavior. And the other end behavior is going to occur to a little to the right of this. They're both pointing upward. And when I'm doing my end behaviors, you always want to work from left end behavior to right. So I'm going to work from the left intercept to the right intercept. Now here's the decision I need to make. I have this end behavior. Is this going to cross through this x-intercept here, or is it going to bounce off of it? Well, here's how you make that decision. The x-intercept here is 1, 2, 3, 4 to the left, so it's -4. So I go to x equals -4. I look at the factor that corresponds with that, and I look at the exponent of that, and that exponent is 1. And as I told you, when the exponent is when the exponent is odd, it crosses. If the exponent's even, it bounces. You need to remember that. Now this exponent is 1. And it's odd. And since it's 1, it indicates that it's a linear. What that means is it's going to cross, and it's going to cross straight through. So let me explain that again. If the exponent is odd, it crosses, and if it happens to be 1, when it crosses, it will cross straight through. There won't be any wiggles because this is a 1. So let's do that. It's going to cross straight through because the exponent's 1. I'm going to cross it straight through like so, and then watch what happens. I'm going to bring it down, and it's going to turn. Maybe right here. Now, this turn was a guess. It might turn here. It might turn here. I don't know. This turn is a guess. So now I need to make another decision. I'm going to draw this, and I need to decide if it bounces off this x-intercept or if it crosses through. Well, I look at the exponent that goes with x equals -2 because this x-intercept is -2. So I look over here. The factor that goes with it is x plus 2. And again, this is odd and it's 1. So when it's odd, it crosses through. If the exponent's odd, it crosses through. And if it's 1, it crosses straight through. So this is going to cross straight through. And then it's going to turn. I don't know, maybe right here. That turn was a guess. It might turn here. It might turn here. So now I need to make a final decision. Is this going to cross through here, or is it going to bounce and come back up? I can tell right away. If I were taking a test, I would know right away that it has to be a bounce because my end behavior is here. So this is going to bounce and come back here. If it crossed through, my end behavior would be here, and that wouldn't make sense. But let me check it to be sure I'm doing it right. Let's go to x equals 1 right here, which is over here. Here's the factor that corresponds with it, and the exponent is even. And when it's even, it's a bounce, so it checks. When it's an even exponent, it bounces. So there we go. This is going to bounce and come back through, and I have a nice sketch of my graph. And this is the general shape of the graph. And I'm pretty much done here at this point. Now, a couple things to remember. This turn was a guess, right? It could have turned here or here. And this turn was a guess as well. Another thing, this y-intercept is a guess. You can actually find the exact y-intercept in this problem if you want to. All you would need to do is plug in values for, you need to plug in 0 for x to find the y-intercept exactly. You'd put a 0 here, a 0 here, a 0 here, and then find out what the y value is. So that's how you'd find the y-intercept exactly. Well, let's continue on to another problem to see how we do on this. Let's go ahead and sketch the graph of this. Do you remember the first step? Well, it's to find the x-intercept. So I'm going to change the y to 0. Right here, and I'll set each factor equal to 0, right? So I'll set this -2 equal to 0. -2 equals 0. That makes no sense at all. -2 does not equal 0. That just indicates there's no x-intercept here. So I really don't need to worry about this -2 because I got this untrue statement here. So I don't need to worry about that. All I really need to worry about is these factors here. I want to put that y back in there. I need to just worry about these two factors because this one didn't make any sense. And I put the y back in place of the 0. Now real quick, I want to tell you one thing. If there were an x here next to this -2, then it would be different. Then you would have -2x equal to 0. And when you solve for x here, you'd have an x-intercept of 0. So if you have an x on the outside here with this coefficient, you will have an x-intercept of 0 right here. Keep that in mind for future problems. But we don't have to worry about that for this problem. So let's just continue and find the rest of the x-intercepts. Well, we really haven't even found any yet. What would the x-intercept be here? Well, it would be -1, right? You just switch the sign of this. What would the x-intercept be here? The opposite of -2 is +2. And let's plot these x-intercepts of -1 and +2. So -1 is here, +2 is here, and now we got to figure out our end behavior, right? End behavior. So we need to find the degree and the sign of the leading coefficient. So what is the degree of this polynomial? Well, remember, since it's in factored form, I can just add these. So 3 plus 2 is 5. 3 plus 2 is 5. So it's the degree 5 polynomial, and 5 is odd. So the degree is odd. And the leading coefficient is right here. The leading coefficient is 2, and the sign of the leading coefficient is negative. So the sign of the leading coefficient is negative. Well, let's go back to our chart here. Degree odd, leading coefficient negative. That's over here, right? Degree odd, leading coefficient negative. My end behavior looks like this, and it looks like this. So let's write those in there. It's going to look like this and this. Remember, I'm working from left to right, and I'm going to put those in just a little better. I like to put it just to a little left of this x-intercept here, so maybe right there is better, and a little right to this. And you should really remember that when you're doing, if the degree is odd, you know that the end behaviors are going to go in opposite directions. So now that we have this, we're getting close to finishing the graph. Let's look at this x-intercept of 1. And remember, I always read from left to right. So this x-intercept of -1, which factor corresponds with that? Well, it's right here. Here's x equals -1. The factor that corresponds with it is x plus 1. And this is an odd exponent, right? It's 3, and when it's an odd exponent, it crosses through. So this is going to cross through, but it's not going to cross straight through. It only crosses straight through when it's a 1. If it's a higher odd exponent, like 3, this 3 indicates it's cubic. That indicates that it's going to wiggle through. So if it's a higher odd exponent, it won't go straight through. It will wiggle through like this. See how it wiggles and then come down. And then I'm going to guess my turn, maybe right like that. This turn is a guess. And then I need to make a final decision. Is this going to bounce and come back, or is it going to cross through? Well, it has to be a bounce because my end behavior is here. So I could quickly finish this by bouncing it and bringing it back here. However, let's check it. This x-intercept is 2, which is right here. This is the factor that corresponds with it. And this exponent is even, so sure enough, when it's an even exponent, it's a bounce. So let's bounce it off. And we are done. This is a nice sketch, a general shape of the graph. And remember, this turn here is an estimate. It could have been higher up or lower down. And this y-intercept is an estimate for this problem as well. We just want to get the general shape of the graph. Couple things I just want to tell you. We're pretty much done. You need to remember that when the exponent is odd and it's 1, it crosses straight through. If the exponent is odd, but it's a higher odd number like 3, 5, 7, or 9, it wiggles through. And the higher the odd number, the bigger the wiggle. And if it's an even exponent, it always bounces. And if it's a higher even exponent, the bounce is not as sharp. It's a more flattened bounce. That would be the difference. Well, I hope this was helpful. Have a great day.